So we're going to start off looking at some of the teaching spaces that we have here in the School of Physics and Astronomy. And we're going to start in these third year spaces. So we have a special tour guide for the third year spaces, which is Professor Michael Morgan, the Head of Physics and Astronomy here at Monash. Hi Michael.
Hi Kay. So welcome everyone. This is some of our teaching spaces. We thought we'd show you some aspects of the collaborative spaces that students meet. These are second and third year students, and this space here, which we'll take you through, is adjacent to our second year laboratories and our third year laboratories, and we'll take you on a tour of some of those laboratory facilities and give you an idea of the kinds of experiments that we can do. So this space here is a great space. It's open from early in the morning to early in the evening, and students come in here. They can collaborate. Often academics walk through, so it's a great informal space, and students find it very valuable for assisting them in their learning. And it's comfortable. Notice that the emphasis is not on computers. The emphasis is on comfortable spaces, seating, lots of whiteboards so they can talk, they can work through problems, they can share their experience,
yes.
Good, bad or indifferent. And we've really found that this is one of these kind of spaces. We've got a whole range of them within the school, indeed within the Faculty of Science, which are really, really helpful for students, because what we need to emphasise in the 21st century, students can get a lot of material online, especially in the current climate. What we as a university are doing is adding to the experience, so providing physical infrastructure, providing collaborative spaces, providing all kinds of vehicles for their learning. So this is really important, because otherwise they can just Google stuff, and that's not how you learn.
Yeah,
you learn
discussions and interacting with each other, and it really gets engaging.
So perhaps we'll walk through and have a look at some of the third year labs.
Thank you.
So this is one of our teaching spaces. This is the main third year laboratory.
Yes.
We have a whole range of laboratories at both first, second and third year. This is the main laboratory for third year experiments, but we also have optics laboratories for third year. Yep. We have a holography laboratory, we have an X-ray laboratory, we have a suite of specialist laboratories, and we'll take people on a tour of this particular laboratory, and then I understand you're taking them on to some of the optics and specialist ones. Now, we're particularly proud of our laboratories because we've invested significantly over the last 5 years in infrastructure and equipment. Literally tens of millions of dollars have been put in to renovate all of the teaching spaces, first, second and third year. And I should add that when we've had external audits of these laboratories by, say, the Australian Institute of Physics, they've been extremely impressed with our commitment to providing resources and the best experience for our students. So,
shall we look at some of the setups?
Let's have a look at some of the setups.
Okay. So what's this one over here?
So this is a Compton scattering experiment, and it's investigating the particle properties of high energy light or X-rays. In fact, this uses a gamma ray source.
Right.
Now, not only is it a fundamental experiment, but it's actually the main basis, or one of the two principal mechanisms for producing contrast in X-ray imaging, like an X-radiograph or a CT scan.
Yep.
But the students are able to investigate how X-rays scatter of materials, and they can do it quantitatively. Now, a number of laboratories in Australia have a Compton scattering experiment. What makes this one unique is this little device here. This is an energy resolve detector, so they can do the full complement of this experiment, not just measure how X-rays scatter, but measure how the energy changes. And this is a beautiful experiment. It was actually built in-house. Indeed, a number of our experiments are built in-house. And the reason for that is that we have, as you well know, because you work in this area of X-ray imaging, we have specialists like Kay who is able to facilitate the building of unique pieces of equipment for our students. And this is
really custom.
Custom, yeah. All right. So this won a Nobel Prize for Arthur Compton. The work was done in the late 1920s, wasn't it? And as I said, it's got practical significance because it's one of the mechanisms whereby you get an image, a CT scan, a computer tomography scan, or an ordinary X-radiograph.
Yes.
Okay, so we have a look.
What about this one making the interesting noise?
This one making the interesting noise. The interesting noise is the vacuum pump. This is a beta ray spectrometer. So beta rays are just very energetic electrons.
Yep.
And this allows students to investigate how electrons with different energies move through magnetic fields, but also it's of historical significance because it really speaks to a particular fundamental aspect of physics, namely that beta ray decay is associated with neutrinos.
Yep.
And although this experiment here is not able to detect neutrinos, it's able to point to the fact that there has to be a neutrino associated with the decay,
right,
of beta ray decay. So
yep,
the really interesting thing about this experiment is that this can be run remotely. So this is a
right,
full-fledged experiment. Students either can come into the laboratory or they can sit in the comfort of their own homes,
yeah,
and run this experiment completely.
Yes.
They can move. You can see that it's totally automated. There's cameras, there's tracking devices for measuring magnetic fields, for changing the source, for changing the magnetic field, and so forth. So
yeah,
it's, and in particular, of course, during the current climate that we
yes,
find ourselves in, having an experiment where students can genuinely engage and run an experiment remotely has turned out to be invaluable.
yeah, yeah. A popular one this semester, I guess.
Very popular. So we have many. We're not going to talk about all of them.
Yeah.
This is measuring the range of alpha particles. Alpha particles are helium nuclei. In
Yep.
fact, they were used by Rutherford to explore and come up with the concept of the nucleus.
Yes.
So the students can explore the properties of alpha particles.
Yep.
Let's just move on to these two experiments here. This is a squid, right?
Not in the ocean, though.
Not in the ocean. So a SQUID stands for a superconducting quantum interference device.
Yes.
And this allows students to investigate the fundamental quantum properties of matter at low temperature.
Yeah.
And again, I should emphasize that although many of these experiments are designed to allow students to investigate fundamental physics, as you well know, and as we tell politicians all the time,
Yeah.
investment in fundamental science leads to important practical applications. So almost every experiment here has got practical applications. But of course, before you have the practical application, you need first to understand the physics, the fundamental physics.
Yeah.
So this SQUIDs are used in monitoring magnetic fields associated with the heart.
Yep.
So instead of an ECG, you can have an MCG.
Yeah.
Also magnetic fields associated with the brain.
Right.
So there are SQUIDs that are used in monitoring brain activity.
Yep.
Now this one here, which looks fairly innocuous, is what's called Brownian motion.
Mm-hmm.
And what the students do is they there's a little glass slide they put under here.
Yep.
And in the glass slide there's small beads around about 2.4 microns, a micron being a millionth of a meter.
Yep.
And they jiggle around.
Yeah.
Now, when this was first observed in the 18th century, people thought that this was some kind of life force because these inanimate things, apparently inanimate, were jiggling around.
Yeah.
It was Brown, the botanist, who realized, in fact, that perhaps what was happening is that the particles were being buffeted by the very, very small water molecules. In this case, it's particles in water.
Yes.
And this motion is stochastic or random. It's called Brownian motion.
Yep.
And it's a fundamental aspect of science. In fact, the work in Brownian motion, which was carried out in 1905, independently by Einstein and by an Australian physicist. Do you remember who the Australian physicist
I don't.
was?
I should know.
No. Most Australians don't even know that in 1905 Sutherland did the same work. In fact, he published it before Einstein.
Yeah.
And the work that Einstein published on Brownian motion is more cited than his work on relativity.
Yeah.
And why is that the case? Because Brownian motion occurs in everything from milk, paints. But here's an even crazier notion. The way that these particles jiggle around is described by an important equation called the diffusion equation.
Yeah.
And economists have found that that equation is also used to model fluctuations associated with what are called derivatives in the stock market.
Right.
This is known as the Black-Scholes equation, but it's nothing but a fancy diffusion equation.
Yeah.
So remarkably, this work here about particles jiggling around in water is also directly related to higher fluctuations in financial derivatives. So this just shows you that you could never have anticipated that someone investigating Brownian motion could ultimately, many years later, lead to insights into financial markets. The take-home message is fundamental science always leads to important applications, but of course we can't predict it, and that's what makes fundamental science so fascinating.
Yeah. And it also shows, I guess, that graduates of the physics program can head into areas like financial modelling from the skills they learn here.
Absolutely. And I mean, a number of my graduates have indeed gone into modelling complex financial systems, the banking system, the finance sector, consultancy. And one of the reasons that they're highly valued is because if you can be creative in one field and you have a deep knowledge, then you can also be trained and translate that into completely different fields, which makes physicists, mathematicians, and indeed engineers highly employable. So even though we don't set out to teach them financial, modelling financial markets, the skills they develop, both practical and theoretical, and also the metacognitive skills that we pointed in this room here, where they learn to work in groups, they learn to communicate and so forth. I think you'll be taking them to the PACE studios, which really emphasises this. So there's many experiments. There's over 25 experiments here that students can choose. This is an experiment called Mossbar Spectroscopy. And this, again, as many of these experiments did, won a Nobel Prize for Rudolf Mossbar. And Mossbar spectroscopy investigates how gamma rays are absorbed. But really, again, this is highly practical. So this experiment that's running at the moment is, and the sample you could use could be something containing iron, it could be an ore. So it could be used to investigate whether a particular ore has a certain amount of iron in it. And so the minerals and mining industry actually employ people to use techniques like this and others to investigate whether it's profitable to dig up a body, because if it's got a small amount of ore in it, it's probably not profitable. So again, this is a fundamental experiment, but practical applications. We have so many more experiments. This measures the lifetime of the muon. The muon is a particle with like an electron, except it's heavier. It's about 200 times the mass of the electron. And right at the moment, your body is being bombarded by muons, which originate from the upper atmosphere in cosmic ray collisions. These experiments here are known as scanning tunneling microscope and atomic force microscope. And this allows students to image structures at the single atom size, at atomic resolution. And it's a powerful technique that it's used in chemistry, in biology, in material science. And again, our students learn the fundamental physics. I should also point out that we have some of the world's most powerful research instruments. So this is a teaching instrument, but we also have research instruments in our research laboratories that use scanning tunneling microscopy. The really interesting thing about this is not only can you image it, but you can actually manipulate the atoms. So you can literally pick up an atom and move it where you like. In fact, one of our PhD students, one of our postdoctoral fellows, Antonia, she picked up atoms and put them in the form of a logo, the logo for FLEET, which is our Centre for Low Energy Electronics Technologies. So again, great experiment. It doesn't use light. It doesn't use X-rays. It uses electrons, but it's not an electron microscope. It uses a fundamental property called quantum mechanical tunneling. So, for example, if I tried to jump, 2 meters, I couldn't do it. I don't have the energy. If an electron tried to jump across a barrier and didn't have the energy classically, it doesn't happen. But quantum mechanically, there's a probability that even though it doesn't have enough energy to get over a barrier, it can actually tunnel through the barrier. This is counterintuitive, crazy stuff, but this is the basis of a whole suite of technology, which again won another Nobel Prize for Binnig and Rohrer in the 1980s. And so we have many experiments. We have over here, this is a PET
Yes.
positron emission tomography, and this is something that we hope that people watching this video never really have to have, because positron emission tomography is standard technique used to explore whether you have cancer. So again, this is using fundamental physics.
Yeah.
So what we have, the word positron is an anti-electron. It's an electron, but it's actually got a positive charge.
Yeah.
And so when you take an electron which has got a positive charge, which is the positron, an electron, and you bring them together, they annihilate and they give off 2 gamma rays.
Yeah.
And these detectors measure the gamma rays. And then you can determine what the origin of those gamma rays are. So if, for example, you have a cancer, you can have a radio-labeled pharmaceutical administered to you that can be taken up at the site of the cancer, and you can image. But actually, not only can you image the structure, you can image the function. And again, this is fundamental physics. This uses antimatter. It uses anti-electrons called positrons. So the source of these, and they're not here at the moment, because we're not supposed to be doing this. We have very strict occupational health and safety protocols, but we would put a source of antimatter here, which is a sodium-22 source, and then that allows students to investigate the properties of positron emission tomography. So we're running out of time, and I'd love to take you through every single experiment and tell you about them in detail. So let's just perhaps wander across here. Just finish with a couple more. This is NMR, which stands for nuclear magnetic resonance. And again, where do you reckon this is used?
Medicine?
In medicine. And what is it called in medicine, Kay? You know this.
Nuclear.
It's called magnetic resonance imaging, MRI.
Yeah.
But so it's actually nuclear magnetic resonance.
Yes.
MRI uses nuclear magnetic resonance. Why do you reckon they've removed the nuclear? Because people are scared of that. But the nuclear here involves the proton of hydrogen associated with water, associated with your tissue. So this experiment here, again, it's another experiment which is being built by staff within the school. It allows them to investigate nuclear magnetic resonance, which is a fundamental tool in medical imaging. Okay, I think we're nearly finished. I'm not going to point out all the experiments. Let me just, before you take them on a tour of the optics experiments, this is a simple electron microscope. I say simple because Monash has got a center for electron microscopy, and it's got some of the world's most advanced instruments. So this is rather simple compared to the advanced multi-million-dollar instruments that you find in the Center for Electron Microscopy. But students are allowed to play with this. In fact, we encourage them to play with all these experiments. One of the things that you gain as a student is when you play with experiments, when you play with ideas, when you think about things, even if you break things, we don't like things to be broken, but it's inevitable, and that's how you learn. So I should also say that in addition to all of these experiments, and we haven't shown you all of them, but students are also able to access experiments in our research laboratories associated with our research platforms like the Center for Electron Microscopy, the Center for Nanotechnology, the Center for Atomically Thin Materials, the Center for Gravitational Wave Discovery, the Center for Astro 3D, Center for Future Low Energy Electronics Technologies, and so forth and so on. So I guess the message is that Monash carries out a wide range of research activities. And that is great for students because they have opportunity to do undergraduate experiments plus research projects in cutting-edge areas, which really helps them in terms of their career.
Absolutely. Well, thank you so much, Michael.
Thank you.
This has been a really nice tour. Very nice to see all these experiments. And I think we're going to move now on to the second year labs.
And I just perhaps will say that we look forward to welcoming you not virtually but in reality. And so if you are interested in physics or indeed astronomy, you may want to consider Monash, and we'd love to see you in person here. Thank you, Kay.
Pleasure. Thanks, Michael.